Good morning. I hope everyone is doing well, keeping warm, and staying safe. Thank you, everyone, for joining us today for today's webinar, Sector Coverage Uncovered. We're joined today by Tasos Alexiou of RF Elements. There is much more to coverage than using the beam width angle as an approximation. And in this webinar, we will explain what coverage really is and the details behind its calculation. There will also be a walkthrough of the updated RF Elements Link Calculator 2.0. So a lot of really good info to cover today. Please submit any questions that you may have in the chat box, and we will cover them at the end of this presentation. And we will also be recording this webinar and sharing it on social media. So let's get started. Tasos, please take it away.
Great. Thanks for having me. Can you just confirm one last time that you can hear me okay?
Yes, sir. Loud and clear.
Perfect. Had some audio issues. Thank you, everybody, for joining. As Jonathan said, we'll be doing our Sector Coverage Uncovered webinar, and we will talk about, again, sector coverage, antenna coverage, and kind of some of the myths, and really to try and give you a better understanding of, where the antenna radiation really goes and how far it goes. At the end, we'll have a Q&A. If you think of any questions while I'm speaking or giving the presentation, please feel free to enter it in the question box now, so maybe you don't forget it by the end, and we'll go to a full Q&A at the end. So, the problem for most WISPs is really, RF pollution. At RF Elements, we really provide innovative solutions for a modern-day WISP. Still today, the biggest problem of unlicensed WISP networks is really interference caused by using gear that was poorly designed and deployed without any regard of sustainability, which is really connected to the RF noise produced by these devices. If a few of these products produce noise, it may not be a big deal. But if everyone produces noise, it really makes it a problem, and everybody really suffers from it. So at RF Elements, we really address the problem of RF noise by really changing the paradigm of the fixed wireless industry. We are really setting new industry standards for RF performance, noise rejection, and system scalability through our award-winning antenna technology with our twist port ecosystem. So let's kind of jump into the topic of beam width versus actual coverage. So these two images here kind of show really the same scenario, but the one on the left is really an overlay of an antenna beam width on a map. Pretty simple. The blue area does not really represent the coverage of that antenna. It simply shows you the selection, the section of a circle that corresponds to the antenna beam width angle on a map, but really nothing more. So this is showing you, the spec antenna beam width of 60 degrees or 30 degrees or 90 degrees. The image on the right is really the closest thing to how coverage would really look. If you could see the electromagnetic waves and they were visible, you would see how they propagate much further, right, than the, again, spec hard number of, 90 degree or 45 degree or whatever the antenna manufacturer puts on the spec sheet. So, while the, electromagnetic waves, really don't have any color, and in order to visualize something, we have to use color. So in this case, we're kind of using red. The stronger signal, the more vibrant the red, the stronger the signal, and vice versa, right? So as it starts to fade away, the weaker the signal is. And in the lower right-hand corner, you can actually see the scale of the signal strength that corresponds to this particular antenna. But really, before we go into the details of coverage, it really would be useful to really debunk some of the misconceptions about what users think coverage really is or isn't. Which is what we'll look at in the coming slides here about beam width and coverage area. So beam width really isn't the same as your coverage area, right? So many users they think and they understand that the coverage of an area is really defined by the beam width of the antenna. Again, that's spec hard 45, 60, or 90 degree. And this is simply just not true. They are connected to one another, but in general, they're not the same thing at all. They're not even close, to be perfectly honest, right? It really is important to be clear about the facts, because sometimes antenna manufacturers use beam width in place of coverage to really give you a simplistic view to a very complex question, right? Which really can do more harm than it can benefit the end user if they really don't understand the differences between, kind of the spec sheet number and the actual propagation of those electromagnetic waves that come out of the antenna. So this is, the number one, misconception of coverage, right? So, usually when you visualize coverage, you're looking at a basic, pizza slice shape, which is the beam angle that determines the angular width of your coverage. The gain of the antenna, how far the coverage reaches is, not that simple, right? So inside the area, we have a signal that has coverage, and then outside the area, we simply don't, right? That's how we've kind of been taught to understand how antennas work, right? But really, again, it's a huge oversimplification of how coverage is in reality, right? The reality is that, the various link calculators really show you some signal strengths, even if you place the pin outside of the coverage area. So how can that be, right? I mean, an antenna is 90 degrees, so it must just stop at 90, right? That's what, again, we've kind of been taught to think and see how antennas really work. So, obviously, there must be some sort of mismatch between what's shown and what's really reality. The coverage for an antenna is not a digital variable. It's not a value of 1 if you're inside and you have signal, and a 0 if you're outside or somewhere else and you don't have coverage. So really, if the beam width doesn't define the coverage, then really what good, is that that number to you, right? What good is it for you for planning if it's really not that simple? So, beam width is an antenna parameter, right? It is, defined by the decrease of antenna gain from the bore site or the center of the antenna by some specific value. The WISP industry, this value is either the -3 or the -6 dB drop-off. These numbers are based on some sort of historical accepted standard, but, really they're kind of arbitrary and closely tied to the maximum gain that anything else to kind of help you give you an idea of what the expected shape of the radiation pattern might actually be, right? So beam width is a very useful piece of information for antenna alignment, right? With very narrow beam width antennas, one should really be precise when aligning, let's say, point-to-point links, because even small deviations can have very strong effects on the link performance. This includes the mounting of the antenna. Narrow beam width antennas should have a more sturdy mounting and should be able to withstand windy conditions, because, again, even a small misalignment can really throw the link off completely as these beams go in and out of connectivity with each other, which directly affects the signal strength of your current link. So, generally, there is no strict point-to-point or point-to-multipoint antenna. Really, the beam width of the antenna is just a good indicator of what application antenna might be better for. Distant, narrow sectors, are possible with narrow beam width antennas. But, because of the higher gain and the more narrow beam width, high gain antennas are mostly used for point-to-point to really squeeze the largest possible link distance for any particular link, right? But you can really use any type of antenna for almost any type of job. It really depends on whether or not it's most suitable for what you're actually trying to achieve in the end. So, in like textbooks about antennas, you can find what the -3 dB beam width angle marks, and what's called the crossover point of two sectors. This is, the point where the coverage areas of the two sectors need to overlap to ensure proper functionality of a network. But as with any, textbook parameter, the default type of, it depends on the type of application. If it's useful for the WISP industry, the usefulness of the crossover points is really negligible due to the unregulated nature of WISP networks, right, in the unlicensed band. I mean, things are kind of, not everybody follows the rules all the time, so it's really hard to kind of, keep these things balanced and matched. So, coverage in reality, we've kind of shown you kind of a short teaser, in our first slides, right? So now that we know beam width is just a very crude and inaccurate coverage measure, we can actually have a look at what it's really like in reality. So there are many parameters that go into visualizing coverage. First, the site. It has a certain height above the ground. It has a specific radio output power. The antenna has a specific radiation pattern and even down tilt, right? And then we need to, map the data and have, enough precision and information of how the AP is oriented on the map. So if we know all these parameters, we can then project the field radiation of the antenna onto a mapped surface, and that's its true coverage. So, you can see that there's really no limit to where the coverage is or isn't, right? It kind of shows you how the signal strength changes with distance, and it has, a continuously smooth decay until the signal strength is below the radio's noise floor, which sets the limit of distance, which, in the end, makes no sense to really display that coverage. So really, the precision of the coverage calculation is limited by the precision of all the input variables, right? So there are also some factors which, are difficult to count on, like, changing weather conditions or even changing foliage in the trees as the seasons change. So all these things really affect what the coverage could really look like when you're trying to plan or look at your true coverage with all these constantly changing variables. So really, a good example of coverage visualization, is provided by visible light, right? So, visible light, is also an electromagnetic wave. So just like, 5 gigahertz RF signals, we can expect, at much higher frequencies, the circular spotlight, let's say, on the ground, which is lit by pointing a light, at a coverage area, we can see this kind of change. So, we expect that the visible light, the electromagnetic waves are invisible, which makes the visualization of coverage by RF really more obscure because you can't really see it out in the field. We have to kind of find a way to try and visualize this for you to make you have the much better understanding of how it works. We can't just do it with text and explanation. We really need to do it with some sort of, visualizations or some sort of kind of coverage, right? So, what we can do though is kind of, again, visualize the RF, in some sort of pseudo color, right? We assign the strongest signal a certain color. In this case, it's red, and then the weaker the signal gets, the more transparent it is. In this example, we're using a 30-degree symmetrical horn, so you can see how the RF dissipates over distance, and you can see how it dissipates in azimuth as you get further away from the center point of an antenna. So you can see it's clearly not, exactly like the 30-degree that you see on the spec sheet. So this dashed line really indicates the 30-degree horn's beam width at the -6, but it's not so. It should be a little bit more clear to you now. Why the signal reaches beyond these lines, right? The coverage is a measure of the whole three-dimensional radiation, pattern and all the other variables that we mentioned earlier. And you can kind of see that there is no color, there's no color border between these areas, where there's signal with and without. It's just a continuously smooth function of the radiation pattern slowly dissipating over distance, right? So for the human eye, a single color, with degrees of transparency is still really not the easiest thing for you to visualize. It's still a little hard to tell what the signal strength is at any particular point. So really to make this plot more useful in practical life, we try to use more than just one color. So here, right, is the same plot that we used using 5 colors instead of just using a single color. Now it's much easier for you to see where the signal is, let's say, -70, and where the signal is, let's say, -45, for example. So the color helps your eyes to quickly kind of estimate the signal strength, what it can be expected and where, right? So if we go in even a little bit further than that, if on top of this kind of AP, output power, CPE gain, we also know what channel width, we're going to use and what the noise floor is, we can still improve, the practical usability of this plot. Even though, again, this helps you see a little bit more where the signal changes, what's usable, what's not, we can actually take it and we have a step further. So in this coverage, these are what we call MCS rate isosurfaces, right? So here, each color determines, right, what is the span of each MCS rate that the link can work with, right? So you all should be familiar with your, MCS9, MCS7, MCS6 for your different QAM rates. We can break this out into very specific colors to show you kind of the transition points between those MCS rates in your coverage area. So this plot really gives you an immediate visual information on what MCS rate you can expect depending on the location of your customer. So now you understand that all these, cases when, setting up a link and wondering, well, how come, you can see the AP, which you should not really based on the beam angle of the antenna that you use, you can see why you can still see it. So, it should, be clear now that using the beam width as coverage approximation is really inaccurate and somewhat misleading. But it is important to understand that all antennas out there function in a similar way, right? The coverage is basically, elliptical shapes, shaped areas, such as we've been showing, but of course differing depending on the shape of the radiation pattern itself for different types of antennas. So let's look at some of the examples here. So, going further, we prepared a few examples of, commonly used WISP antennas to kind of illustrate to you how the coverage looks based on the real physics-based data and simulations, right? So we can start here with a sector antenna. So, the traditional sector antenna has a very wide radiation pattern. The coverage is not defined by the beam width at all. You can see the back radiation, the side lobes that cause all the issues with co-location with these antennas very clearly when you look again at the coverage area and the different MCS rates from a standard antenna. We can take it a step further and look at the same type of patch array antenna with these shield kits, right? So a lot of people, in the hope of mitigating some co-location issues, many WISPs turn to all kinds of shields that they install to the back of the antenna. So while the shield might really help dampen some of the back radiation a little bit, you can really see what it does to the rest of the radiation pattern, right? Its shape ends up being rather wild, and potentially making your life more difficult because, the customers who work close to the edges of the sector can find themselves all of a sudden out of coverage. So, these shields are really, really not a good idea when trying to deal with noise because, for example, in this case, the back radiation, didn't really change much and the main lobe has changed substantially, right? So they really disform or change the beam pattern that's out there and makes it very difficult for you to figure out what your coverage area really is and where the radiation is really effective for your customers. So, our symmetrical horn antennas have no side lobes, which you can clearly see from this plot, right? So it's really a nice pill-shaped beam, just pointing forward, right? So, let me say again, these are not images, somebody just created in Photoshop, right? I know it's a static image here, but these are real physics-based simulations, right? Which is the closest thing that we can get to reality. So this is not just a, let's put some colors out here to give you, some sort of idea. These are the actual beam patterns based on the antenna specs themselves. So, the same really goes for our asymmetrical horns, right? So, here's the coverage when using an RF Elements 90-degree asymmetrical horn. And again, any antenna, would give similar results, but there are multiple MCS zone widths and beam width angles, and the signal does not, the signal goes beyond those angles as well, even, with our horn antennas. Oops, sorry, I went too far. 1 second. Sorry. So, really similar images can be produced for point-to-point antennas as well, which, we'll show here more obviously that the coverage is much more than the beam width alone, right? So, among all directional antennas, a dish is the most common one used in the WISP industry. You can kind of see how the coverage looks using, this particular dish. Besides the substantial difference between the polarizations in terms of the side lobes and undesired coverage, you can see that there's really a lot happening outside of the manufacturer's declared 5-degree beam width, further confirming that, really the coverage of an antenna goes way beyond the beam width, definition in the spec sheet. So again, kind of just trying to reiterate this, dish antennas are mostly misunderstood because everybody fixates on that, 5-degree, 4-degree, 8-degree main beam width. But really, when you look at all the side lobes and where the radiation really goes from that antenna, it's typically much, much wider than you think, right? So, looking at the real coverage plot, more can be said about the antenna. Like in this case, the directional patch array, side lobes are very clear, right? As well as the chain imbalances, right? So each of the polarizations have quite different coverage shapes. So again, here we're kind of showing you, the horizontal and the vertical beam pattern, right? So again, the antennas aren't always matched in both polarities. So one polarity has one pattern, the other polarity has another pattern when you're looking at these directional patch array types of antennas. So really, the optimized design of, RF Elements ultra dish antennas really help minimize the side lobes to a large degree, right? But the physics of dish antennas really dictate that, side lobes are very hard to avoid completely. So, nevertheless, our ultra dishes are optimized for minimum side lobes. So they still exist, but you can see that we try to minimize the side lobes as much as possible, but you can't escape the physics of a dish antenna or a patch array antenna. Side lobes are just inherent to those types of antennas. So, here is our ultra horn, right? No side lobes whatsoever, just a single beam, and that's it. So it behaves, in a similar manner to, like, let's say a flashlight, providing a very clear coverage with no side lobes, creating unwanted coverage areas, and really its performance is identical in both polarities, which is why, we're actually able to plot only a single pattern. And it shows you both what horizontal and vertical both look like because they're identical. So really important to note, one of the main parameters in designing all of our horn antennas is ensuring that both polarities match. And this is a very difficult task, and we spend a lot of time to make sure that vertical and horizontal gain, vertical and horizontal beam patterns are as closely matched as possible, and in a lot of cases, identical. So Really the plots on the previous slides are really showing only static images of the coverage, in one particular frequency, which is again something that's really important to understand, even when you read spec sheets, right? In spec sheets, you're looking at some hard-coded parameters for gain, beam width, and all this other stuff, and it's typically at a particular frequency, right? So if we were to calculate the coverage at many frequencies, right, and make an animation of these images, then we could see how the coverage changes with frequency, which is something you typically don't see in a spec sheet, and most manufacturers never really talk about, right? So it's really very important information for a WISP, since you use a very wide chunk of spectrum. Therefore, the antenna performance, in this case of coverage, should be ideally stable over the entire bandwidth. So it's really important, that you have, a very stable patterns as the frequency changes. So the frequency dependency of these antennas is something that you really should consider when you're purchasing an antenna. So, seeing this animation, really might not surprise you, because you probably experienced this in practice, right? Where, you're switching channels, hoping to use a cleaner bit of spectrum, and the results seem even worse, leaving, kind of you scratching your head. It's like I had changed a channel to something that was clearer, but I'm not really seeing what I'm supposed to. So this is exactly what happens when you're changing channels. The radiation pattern is changing a lot with frequency, causing fluctuations and ultimately unreliability of your network. And it is, really, unfortunately, the properties of a patch array antenna that does this. So, this is what we mean when we say that, the coverage is not stable or reliable. The frequency dependency of the radiation pattern makes the user experience anything but satisfying, and your life as a WISP constantly busy servicing links, that are changing whenever you switch channels. So again, you can see as you kind of sweep through the frequencies, your coverage area is changing because there's certain frequencies where some particular antennas just aren't optimized to be in. So yeah, they may have, they may cover the whole 5 gigahertz spectrum, but they're not giving you the same exact performance that you see on the spec sheet. And typically, the antenna manufacturers tend to pick, the best performing, the single frequency where they can optimize and get the best gain, the specific beam angle they want to market towards you, VSWR, and all those other parameters. And then as you start to deviate from that one frequency, you can see how it really starts to change, right? So, this is how, the RF elements patch array sector performs, right? So the coverage fluctuates somewhat, as you can kind of see. But, overall, it's much more stable than most antennas of, the same type, patch array sector antenna. So, visualizing the coverage, like this really tells a story of what a stable coverage area should look like. So as you can see, we spend a lot of time in designing our antennas, even when it's a patch array sector, to ensure that we're giving you, again, the best performance across the entire spectrum. So as you change channels, you can depend on the performance no matter what part of the frequency band that you're actually in. So, even more, right, you see this with our horn antenna. So, if our patch array sector was stable, then horns are really super stable, basically. So within the spectrum, the coverage is virtually unchanged, right? So, which is what you really want from any sector or directional antenna. This is the way you can really rely on its performance and provide a kind of headache-free service for your customers. It really is, a dream for every WISP, right? Is again having a performance you can count on, and patterns that are reliable, even when you're changing, some input parameter, specifically frequency, right? So, really, our asymmetrical horn antenna pattern, coverage patterns are really, as pretty much as kind of as good as it gets, right? So, our symmetrical horn is really a very different case from anything else as well, right? So it provides extremely stable coverage, within, again, the usable spectrum. So, this really is a great advantage of horns, right? As, a type of antenna, it's their stability. But, really don't be fooled, right? Not all horns are stable, right? So, a horn can be designed for such, stability, but it really takes a lot of considerable effort to achieve this. It really has to be something that the antenna manufacturer really wants to focus on, like we do at RF Elements, to ensure that these parameters are, as stable as possible, and picking the right type of horn antenna, and then modifying it and tweaking it, tweaking the design to give you this stability. Just because it's a horn doesn't mean you'll see this type of performance. It's RF Elements horns really right now that bring this to you, right? So, another parameter which is often overlooked is, really down tilt as, really another functionality of RF Elements horn, right? So unlike patch array antennas, and from the following slides, we'll see how down tilt really, as a function, works with RF element horns compared to other antennas. So we saw as we change frequency how unstable the pattern is for different antennas, but something that's really misunderstood is how down tilt influences your coverage area again, not the spec beam angle, but the true coverage area of an antenna. So again, down tilt is really a huge factor influencing your coverage area, right? So, at least with patch array sectors or any other antenna with a very narrow radiation pattern in the elevation plane, right? So from this animation, you can see that anything beyond a few degrees of down tilts really makes the patch array pretty much useless, right? You don't have to you go more than 4 or 5 degrees, and the pattern or your coverage area pretty much just starts to disappear, right? So in other words, again, you lose your coverage almost completely. So this really is a disadvantage of very narrow radiation patterns in the elevation plane, right? And why traditional sectors require very precise setup, for down tilt, and they are very sensitive to even small deviations from down tilt when you set them up. So asymmetrical horns have a strong advantage of gradually shrinking the coverage area when increasing down tilt. So while we're retaining the shape of the coverage area, so this kind of smooth coverage area shrinking, from 0 degrees to 25 degrees of down tilt is yet another tool, or additional functionality in your hands when you can help mitigate the noise your radio sees and respond to changing customer bases, depending on where the further customer is located. So again, when we adjust the down tilt on our asymmetrical horns, again, it's not almost binary where you have coverage and you don't. We really give you the precise ability to increase down tilt and slowly creep your coverage area closer and closer to the tower, and therefore giving you really precise sorry, I'm at a loss of words here. Giving you kind of really precise ability to put the coverage where it is and minimize your radiation at the horizon, and therefore reducing the noise that the radio sees while still keeping your customers in coverage. With our symmetrical horns, the effect of down tilt is also a totally different game compared to patch array sectors, right? So, progressively increasing the down tilt, you can see the gradual shrinking of the coverage area while its shape is really completely preserved, right? So the shape is really not changing. It's just, slowly getting smaller and smaller as you add more and more down tilt. So this is yet another advantage of our horns. By using the down tilt, you can dramatically improve, the noise conditions for your network by simply setting up the down tilt based on the furthest customer throughput requirements, right? So this way, the antenna only delivers and receives signals from as far as necessary. So again, with patch array sectors, it's almost binary where you put a little bit, 1 degree too much, and you kind of lose your customers at distance. With our horn antennas, the gradual decrease and change of coverage area allows you to, again, fine-tune your coverage area minimize noise and maximize gain to your actual customers out in the field. So here you can kind of see an example of how to use downtilts, right? So if your customers are clustered, closer to the site, and you have competitors out there that are further away, you can set the downtilts, in such a way that the MCS zone you want, to provide customer coverage at your CPE. So you can slowly start to tilt it down, right, and nullify the noise that's out there, but still maximize the MCS zone for the customers you actually want to keep. So this principle is actually valid in general, regardless of whether, you have competitive CPEs out there from another WISP or something like that. Just, set the down tilt according to your CPEs that's, the furthest away for that particular coverage area. So it's really quite simple. If you're wondering how to really figure out, the down tilt you need to use the leverage of this feature, we have a really, really nice link calculator that we put on our website that helps you not only visualize the MCS zones in color like you've seen in this presentation, but in real time it allows you to plot your customers out there, pick the particular antenna from us that you want to use, and then you could start adjusting the down tilt and seeing, again, the kind of MCS rates change and the coverage areas for those different MCS rates as you start changing it. So, now you can really have a look, and we'll kind of show you how the new calculator works, and we can give you a little demo here real quick. So hold on a second. If you want to take a picture of this, you can. It's a QR code. It's really easy to find our link calculator. It's rfelements.com/calc. I can kind of show you a little demo of the calculator if we want. Maybe we'll save it for the Q&A section. So let's just finish these last couple of slides, and then we can kind of move into that to take questions, and I can kind of show you how that works. So, really, education is just as an important aspect of what RF Elements kind of does, right? It is important to have high performance hardware, and at the same time, it's important to have an understanding about how to use it correctly and how it works, which is why really user education is important to us, and and all of our kind of awareness activities that we do, right? So it is, one of our many first time in the WISP industry type things that RF Elements does and we put on display. So it's not really just about us making a unique antenna and bringing kind of this new ideology of noise reduction and different types of antennas, but it's also something that we're kind of, pioneering in this industry to really help educate the user base, because our idea is that only really educated customers can make qualified decisions, right? And we are also very open about myth busting things, right? Because there are many myths and misconceptions in the wireless industry that really create big problems for many users. So we find it as an important part of what we do is trying to help WISPs understand and visualize how RF works, because it's invisible to most people. So that way, a more educated user base builds better networks and makes for a really stronger industry as a whole. So, join our community online. We're all over social media, Facebook. We have an active forum, a lot of information on Instagram and Twitter and other places. So you can find us and find information about our products. A quick trademark disclaimer here. So, we use third-party trademarks in this presentation solely to state compatibility with our products. All rights of trademark owners are reserved. For more details, check our product disclaimer on our website. And with that, we'll go to Q&A, and then we can kind of take you through a quick test drive of the link planner that we have, our link calculator on our website. So, Jonathan, I don't know if you want to chime in here and see if we have any questions. We can start asking some questions.
Excellent. Thank you for going over all that info and for these the really easy to understand interactive slides too. A few questions did come up. Let's see here. Some of them we may have touched on, but we can review the answers once again. Some are regarding sector antenna coverage and some specific to RF elements. One of them is, what is your opinion on dual band sector antennas, such as 3 gig and 5 gig? And is the coverage of these combined sectors the same as deploying two separate sectors?
Yeah, so I don't like them. It kind of depends, right? So some manufacturers really try and make really wide band sectors that cover, too wide of a frequency band. And like we kind of showed in some of the animations, the spec sheets for those are usually really misleading, because they're picking a specific frequency to highlight the best operating parameter in that particular frequency band, to sell you an antenna, but you really don't know what it's like as it sweeps through the entire band. There are some dual band antennas which actually have two co-located sectors. Those are better, right? So you have an independent, hopefully better tuned and matched antenna for, let's say, 2.4 gigahertz, which is standalone. And then you have another totally standalone, hopefully optimized sector for 5 gigahertz. That's a much better option, I guess, to go with. But trying to find a single antenna that works from the 2 gigahertz up to 5 gigahertz, I mean, I'd stay away. It's really difficult sometimes to kind of push the point we're trying to make. There's a huge not misunderstanding, but there's a huge kind of misconception or an allowance of performance that people have when we talk about how antennas work. And there's a difference between something that works and something that performs, right? So yes, you can build a dual band antenna that does 2, 4, and 5 in the same patch, and yeah, it's going to work, right? But is it really going to perform and be optimized for any of those two bands? I say no, right? So I can build you, a coat hanger antenna that will somewhat resonate, and your 2, 4 CPEs will connect to it, right? And your 5 gig, will connect to it, and it'll work. It'll pass data, but it falls apart over time, right? Over distance and all the other stuff. So really, I think what people should really be looking for are solutions that don't work. We should be looking at solutions that really perform. So again, that's my personal opinion. I don't like them. But sometimes people have to do what they have to do. I understand that side of the argument that WISPs often have, kind of like I think everybody that knows me knows how I feel about omnis, right? And it really kind of comes down to that, that sometimes you just got to do what you got to do. So
excellent.
Hopefully that answers it.
Yeah. Sure. Another one that came in is, what is the best way to ground the RF element antennas?
Good question. It'd be through the housing itself. So I would go ahead and ground it under any of the mounting bolts on the mount to wherever your ground, your ground cable is that you're using. So we don't often have people grounding the antennas themselves, but yeah, there's no ground screw specifically. So yeah, I would just use one of the main bolts that are there for the mounts themselves.
Okay. Is RF Elements planning on releasing any CBRS sectors or horns?
Yes.
Oh, that's really good news. That's great news. All right. Will our future RF element antennas cover the lower 6 gig band?
So we currently do, right? So you have to, again, look at our spec sheets to see the range. So our symmetrical horns, right, they're the first horns that we came out with, the smaller round ones. The symmetrical horns already work up to 6.4 gigahertz, so you're covered already. Our asymmetrical horns, I believe, stop at 6. I'm not sure about our newest array sector. We have a new patch array antenna that we just put out. I don't remember what the spec sheet says on that, but again, if you go to our website, it's all there. As far as the 6 gigahertz band, depending on how it all hashes out, in the end, there are probably will be a whole new SKU for 6 gigahertz. Especially as we get above 6.4 and we start going closer to 7 gigahertz, it'll probably be a new SKU. Really, it kind of comes down to what I talked about earlier in some antennas, right? On having too wide of a usable bandwidth for the antenna. Sure, you could use them beyond 6.4, but it's really hard to, again, make an antenna that performs, and that's what we do at RF Elements. We make antennas that perform at the spec frequency. So yes, we could make it work, but we rather make it perform. And in order to do that, we think that for the, again, 6 gigahertz, we will probably have a whole new line of horns and stuff for that particular spectrum. But again, sorry, I kind of talk and ramble sometimes. The symmetrical horns right now work up to 6.4, so you can start using the symmetrical horns right now and kind of get your feet wet with that new frequency range.
Great, thank you. At what distance from the tower is using a sector over an Omni the best choice? And I know you touched on this briefly. But...
Yeah, I mean, that's too generic of an answer, right? Or of a question in order to answer. I mean, what's the output power? Are you in DFS, non-DFS mode? What's the gain of your Omni? What's the gain of the sector? You can't really answer questions like that without having all that information. What I would say is, go ahead and use our link calculator, and that's the best way where you can input, the frequency band, the TX power for the radio to meet EIRP for either Uni 3 or DFS, and it also depends on what CPEs you're using, right? So an Omni might be effective out to 2 miles with a nano beam, let's say, but if you're using a Rocket AC with a 30 dBi dish on an Omni, you're going to go 2-3 times as far, maybe, right? So it really depends.
Okay. Will a radome for the Ultra Dish 550 be available in the future?
So yes, we have a new Ultra Dish that will be supporting radomes. We have a higher gain one coming that's going to be about 30 dBi. The 550 will have a radome. I believe we will have support for the 400 as well. I'm not sure yet. And we even have a smaller gain one coming as well. So yes, radome support for our Ultra Dish in a size that makes sense to have a radome is coming.
Excellent. Production team has been busy.
Yeah. Well, it's been tough kind of catching up after COVID, trying to get our current product line back in production again and stock moving, and then kind of, building the stuff we promised last year, right? I mean, we should have had this stuff the beginning of 2020, and then COVID happened, so it's making it difficult. But yes, we're getting there. We're really close to a lot of things.
Awesome. When would an RF element sector antenna be preferred over an RF elements horn?
Again, it kind of really depends. There's really no kind of binary answer for that. I mean, really, I get the question a lot. Well, if horns are so great, why are we still making a sector? Why did we spend the time to make a sector? And really, the argument really comes down to cost. There really is a huge portion of the global market that's extremely, extremely price sensitive, right? And sectors are easier, cheaper to make. So I would say if you're trying to cover a very large area with low density of customers, if financially you don't have bigger budgets or big enough budgets to kind of pay the price for our asymmetrical antennas, then probably the sector is right for you. I mean, quite honestly, the argument often for an Omni is, again, low density, low cost. As you saw with the radiation diagrams of the actual coverage of antennas, you could probably get away with 2 sectors and 2 radios, right? 2 of our sectors and 2 radios to kind of give you the coverage you need in place of an Omni, right? It would give you much better performance, much greater distances. So I would say that the sector is a great kind of stepping stone for your first steps away from Omnis. in low density, and then as density builds, then you can replace those sectors with horns and kind of build out from there. It's a complicated thing. There's a lot of variables to consider, when you use one technology over the other, but cost is usually the driving force behind a sector versus a horn.
Excellent, thank you. And quite a few other questions did roll in as well, but since we're a little low on time here, we will go ahead and when we post the video, we'll post all the answers as well. So I'll be sending them over to you, Tasos, so that we can get those answered. Did you want to go over the link calculator a little bit?
Yeah, let me give me a second here.
Excellent.
Can you still see my screen?
Yes, sir. Actually, it's all blue right now.
Yeah.
Okay.
Exactly what you're supposed to be seeing.
Perfect. Beautiful.
All right. So here we're looking at a 30-degree symmetrical horn that's running out of EIRP. So we'll change that here, and let's play with some cambium gear riddle here. Let's just go with 300 here at standard, like some 25 dB gain or something like that. So we'll give it time to render the MCS rates that we had talked about here. My luck, is just going to sit here and not do it now. Come on. It's usually much faster than this. Give me a second. I don't know what to do. There we go. Okay. So here we can see a 30-degree, again, symmetrical horn at EIRP. And we can see, again, the kind of pizza slice, that's that spec 30-degree that you see on the spec sheet. But here we can see the MCS rings for what you can expect at particular distances. Let's go here to miles. So you can see this CPE here is at 6.6 miles and still maintaining an MCS 8 connection. You can easily add more CPEs and move them throughout the coverage area and see what kind of signals you should get and where they're at. Again, we have the ability to turn on and off the MCS rates that are usable to you. In a 256 QAM type radio, you really shouldn't be going below MCS 7. Of course you can. 64 QAM is MCS 7, so we kind of turn off these because this is really usable. Even though you'll get signal out here, you probably wouldn't like those speeds. But again, you can kind of see here, we can start adjusting down tilt here, and it will recalculate for you, and you could see how far you can go with down tilt to, let's say, keep this one customer, sorry, at the maximum MCS you want, which we said 7 is probably, sorry, I apologize. MCS 7 is probably the lowest that you want to ever have, right, on a 256 QAM radio. So again, you can start playing around with this until you kind of get to where that coverage is and where that crossover point is that you can stop. And therefore, with 13 degrees of down tilt, you've now made that AP much more noise immune to the noise coming in from the horizon because you've turned down the gain. So you can see here, somewhere between 10 and 13 is kind of the crossover point to keep this guy within MCS 7. Again, as an example, we can actually go to the fuller screen here, might be a little bit more useful. Satellite view here. So again, this is just some really cool features within our link calculator. Again, we have populated it with a lot of manufacturers out there, their radios. The more detailed radios like Mimosa and Cambium, are listed here because Cambium and Mimosa actually worked with us and shared all the information that we needed for receive sensitivities at the different MCS rates. Unfortunately, companies like Ubiquiti don't, so it's very limited, and we had to work off the generic information that's in their spec sheet for these particular radios. We're working on getting Microtech in here, but typically, if you don't see your radio listed, you can pick the kind of generic 802.11n standard or AC standard for whatever radio you're using, and this will give you kind of a general idea of what the receive sensitivity crossover points are for each of the MCS rates and stuff like that. So as you pick different subscribers, again, it'll change, it'll re-render and change here. Again, by picking these integrated units from manufacturers like Cambium or Mimosa, again, it already factors in the gain of those antennas, and as you change it, again, it will re-render and change what the MCS rates are for those particular devices based on the key device that you use here. So you can change it. Like I said, this if we went here and change this down to, like, let's say a 19 dBi antenna, you won't see this pattern change because this pattern is based on what a 25 dBi antenna would see at that distance, right? So if we change and make CPE2 our primary, which is a much lower gain antenna, you'll see that the coverage area changes. Again, this is something that, people often don't think about. The intensity of your signal at distance depends on the CPE that you're using. More gain, means, higher signal. So this doesn't mean that this CPE won't see this AP good. It's just showing you in reference to what the gain of this CPE would see if you're using that type of device. I hope that makes sense. But again, we could only visualize based on the link budget of the AP and one particular CPE, right? So if you use all the same CPE, force 325 throughout your coverage area, then you should be fine when you pick that one, and it'll kind of show you. So again, you can kind of move it around, and coverage can change. You can again change your antenna type to asymmetrical or symmetrical, and it will plot out again what the ISO tiles are for all the different MCS rates, so you can see what your coverage looks like. Again, increasing and decreasing gain, downtilt, and again, adjusting your TX power to stay within EIRP standards for whatever frequency regime you're in. So you can also now import CPEs. So we have this new feature here. I believe you can only import up to 10 CPEs, but if you have a KMZ file, you can map out, let's say, 10 of your customers. You don't have to map out the whole entire field, but maybe you can pick 2 or 3 of your close-in customers, 2 or 3 of your mid-range customers, and 2 and 3 of your farthest range customers to import them, and therefore you can kind of get some sort of distribution here to see what kind of signals they would see at those particular antenna types and those particular specs for those particular CPEs and stuff. So pretty cool tool. Also, last thing I'll add is that down here we have a really cool video that we put together, which is a full tutorial on how to use it. So it explains all the different parameters and how to adjust them and how to read and see, again, what MCS rates you should see, what kind of receive powers you should get, and stuff like that. And then you also have the ability to do point-to-point if you want as well for a single CPE. And this will show you the terrain profile, again, what signal you should see, and so on and so forth with every device that you use. So that's pretty much it for that.
Wonderful. That's a very well put together complementary tool for everyone to use, and I hope everyone takes advantage of it, of the new link calculator available right on rflms.com. So thank you very much again, Tasos, for putting together this presentation. We will be posting a recording of this webinar for anyone that might have missed it or would like to rewatch it. So please make sure to like us on Facebook at facebook.com/ISP Supplies, and also subscribe to our YouTube channel at youtube.com/ISP Supplies. For all the latest webinars, video blogs, instructional walkthrough videos, and much, much more that we can be uploading there. For additional information on any needed network solution, please give us a call at 855-WISP-PRO. That's 855-947-7776, or shoot us an email at sales@ispsupplies.com, and one of our sales engineers will be happy to assist. So I'd like to wish everyone a wonderful rest of your week and stay safe out there. God bless everyone.
Thank you. Bye.
Thanks.